Hello ECA students, welcome to week 2 of nuclear chemistry. This week we are focusing on radioactivity. You're going to have a quiz based off this slideshow for 20 points and a reading response for 20 points based off topics relating to this week's theme. Topics in this slideshow are going to cover these things, and here's our objective and essential question. Let's start with the history of radioactivity. Some of the greatest discoveries in scientific history were purely on accident, including penicillin and my favorite, chocolate chip cookies, as well as radioactivity. French scientist Henri Becquerel discovered spontaneous radioactivity in 1896. Let's call him Henry B for short. Becquerel is hard for me to say. Henry B was very interested in the recent discovery of X-rays and fluorescent minerals, and he happened to be a photographer. Combine all those things, he had an incorrect hypothesis that uranium salts he had been studying might absorb sunlight on photographic plates and re-emit them as X-rays. To test this idea, he took a photographic plate, or you can think of it as photographic film, and then placed uranium compounds on top of the cutout shape, and then placed that on the plate and took it outside. When the plates produced an image or an outline of the shape, he thought his hypothesis was correct. Like all good scientists, he repeated his experiment, but during that time it had been cloudy for many days during that February month. Deciding that he couldn't do his experiment without sunlight, he put his prepared plates in a drawer. He later opened the drawer and developed the photographic plates, expecting to see really weak images. To his surprise, the images were perfectly clear and beautiful. He discovered that the uranium compounds emitted invisible radiation on their own without the help of sunlight. Pretty cool. All right. Marie Curie did not discover radioactivity, but she did give it its name and provide many discoveries about it. She discovered radioactive elements such as polonium, which was named after her homeland, Poland, and radium. She created a measuring system to determine radioactivity's intensity, and her lab partner was actually her husband. The Curies shared the Nobel Prize in 1903 with Henry B. However, the Curies were both very poor and did not have a lot of protective equipment that they should have had, and Marie Curie unfortunately died in 1934 of leukemia due to the high exposure of radiation. While all elements have some radioactive isotopes, these 37 elements have no stable isotopes. They have unstable nuclei and are naturally releasing energy through radioactivity in order to reach a stable state. Notice they include the heaviest elements on the periodic table. They have very large numbers of neutrons, more so than they do have protons. For example, uranium-235 has an atomic mass of 235, but has an atomic number of only 92. 92 of the atomic number also states the number of protons. So we have 235 minus 92 equals 143. So uranium-235 has 143 neutrons and only 92 protons. That doesn't seem very balanced to me. Since radiation happens to be on the atomic level, it must be measured indirectly. Radiation can be measured at the source or at the place of absorption. Henry B. discovered radiation exposure to photographic film is proportional to the amount of time and exposure, so radiation can be measured by film and can be used to measure the recorded exposure of radiation of people. Here's a picture of a tool called a radiation monitoring badge that many medical workers wear that uses photographic film to measure that exposure. Another type of radiation measurement is an ionization counter. We know ions as positive and negative charges, such as electrons or protons or sodium plus or Cl minus. An ionization counter measures the ions produced by radiation. Geiger counters are a type of ionization counter. So in a Geiger counter, radiation is received through a tube that is filled with an inactive gas, such as argon, that acts as an insulator. You know, an insulator is something that's not good at conducting electricity. An insulated wire inside the tube is connected to the positive terminal of the direct current. So the positive terminal, and there's your insulated wire. The metal cylinder around the insulated wire is connected to the negative terminal. So this metal cylinder, there is not a current between the center wire and the metal cylinder. All right. When radiation passes through the cylinder, this little zigzag arrow right here, it ionizes some of the gas atoms of that argon, releasing free electrons. Boom, boom, boom. These electrons are accelerated by the field between the wire and the cylinder, and the accelerated electrons ionize more gas molecules, so kind of like a chain reaction effect, which results in a large number of free electrons. This creates a current, and that creates electricity. And it also kind of creates a pulse. And when connected to a speaker, that pulse is heard as like little click or pop sounds. So if we were in person for learning nuclear, I would have you use Geiger counters and measure radiation around the school on a scavenger hunt. And it would tell you, it's kind of fun. I did it at another school. I wish we could have done that. All right, moving on. Radiation exposure. So medical x-rays are the single largest source of man-made radiation exposure. This is why dentists place a lead blanket on patients receiving x-rays of their teeth. And this is why you insert a proper shield between you and the radiation source. This will greatly reduce or eliminate the dose you receive. Background radiation exposure includes cosmic radiation. Radiation levels increase as you get closer to the source. So if the source is the sun, that means the higher elevation you are, the closer you are to the radiation source. So the higher the altitude, the higher the dose. That's why living in Denver, Colorado, at our high altitude, people receive a higher annual radiation dose from cosmic radiation than someone living at sea level. Terrestrial radiation levels vary by location, but areas with higher concentrations of uranium and thorium in surface soils generally have higher doses. So that just depends. Our bodies contain small amounts of radiation because the body metabolizes the non-radioactive and radioactive forms of potassium and other elements in the same way. All right, to protect yourself from dangerous radiation sources, you need to take into account time, distance, and shield protection. So limiting exposure time reduces the radiation dose received, and increasing distance between you and the source decreases the dose of radiation exposure. Barriers of lead, concrete, or water may provide shield protection from gamma rays and X-rays. All right, important uses of radiation in medicine can be, but are not limited to, radioactive sodium, used to detect blood clots, radioactive cobalt isotopes, used to kill cancer cells, also known as radiation therapy, radioactive iodine isotopes, used to study thyroid functions, and gamma ray sterilization of tools. Other important uses of radiation are food preservation, called irradiation, genetic engineering, and pesticides, one example is sterilizing caterpillars, and nuclear gauges are used in industry a lot. But last but not least, very important, inspiration for sci-fi comics. Can't forget that. All right, so say we have a sample of an element that is 100% radioactive. It has 100% radioactive isotopes, meaning that all the nuclei in the sample are unstable isotopes. These nuclei need to go through radioactivity to become stable. Radioactive isotopes decay at a certain rate, and we measure this rate with a measuring system called half-lives. Half-life is the amount of time it takes radioactive isotope mass to decay half of its mass into more stable isotopes. It's measured as It's measured as mass lost over time. So let's look at a visual. Here we have a mass of radioactive isotope. And we split it in half because over time it will decay into more stable nuclei, and half of it's still radioactive, but half of it has decayed. So we end up with only half of the radioactive isotope left over time. And if we do that same amount of time, we will have half of that amount is still radioactive, and the other half has been decayed into something more stable. So in its half-life, meaning half the mass is gone, we will have a certain amount of time that happens depending on the isotope. So some half-lives can be less than a second, and some can be billions of years, depending on how radioactive it is. If a nuclei is really unstable, it's going to be more radioactive and therefore have a shorter half-life. So you're going to have a question on your quiz. If isotope A has a half-life of seconds and isotope B has a half-life of 1,000,000 years, which isotope is more radioactive? What do you think? What are you going to say? Let's look at an example. A really useful example of half-lives is called carbon dating. Carbon-14 nucleus is not stable as carbon-12 or carbon-13. It will take 5,700 years for half of a sample of carbon-14 to decay into carbon-13 or 12. And it will take another 5,700 years for that sample to decay half of the remaining carbon-14 mass into more stable isotopes and so on. So carbon half-lives are especially useful because living organisms carry a certain percentage of carbon-14. And when the organisms die, that carbon-14 decays over time. We can use this information to find out how old fossils are through carbon dating. Pretty neat. All right, so let's do some half-life calculations. Let's look at iodine-131. It has a half-life of 8 days, pretty short. And if we use 2,000 pounds of iodine, if we have 2,000 pounds of iodine-131, how much will we have in 32 days? So let's use our little visual again. In 8 days, half of the radioactive iodine-131 mass will decay into more stable isotopes. So say we start off with 2,000 pounds. In 8 days, we'll only have 1,000 pounds. And in 16 days, that should be 500, we will only have 500 pounds. In 24 days, so 8, 16, 24, 8 plus 8 plus 8, we will have 250 pounds, which is half of 500. And then in 32 days, we will have 125 pounds left of radioactive iodine-131 isotopes. So that's pretty quick. In 32 days, if we had 2,000 pounds, and then in 32 days, 1 month, we only have 125 pounds. So we could use this setup to solve for all of our equations if we want to, but we can also use, we can use this diagram to solve all of our problems if we want to figure it out, but we can also use this equation, which is not as intimidating as it looks, I promise. So here's that equation. We have A equals A sub O times 1/2 to the power of T over H. What does that mean? The A is the remaining mass. We can think of that as remaining amount. The A can stand for amount. AO is the original amount. O can stand for original. So what you started off with. T stands for time. That's how many, so we had 32 days. That's going to be our time. And H is the half-life of the isotope. All right, let's put that into play. AO. Original amount is 2,000 pounds of iodine-131. Our time was 32 days. Our half-life was 8 days, and we need to solve for our A, our remaining mass. So let's plug and chug that into our calculator. A equals 2,000 times 1/2 to the power of 32 over 8. And we get A equals 125 pounds. So it's not too bad. And if you have any questions, please don't hesitate to email me and I'll help you with it. That is the end of this slideshow. If you have any questions, please email me. And good luck on your quiz. Bye!